We're going to take a look at another way to prove that a quadrilateral is a parallelogram. This theorem is a little bit different because instead of using two pairs of opposite sides that have some common trait or two pairs of opposite angles, I'm actually just going to look at one pair. So what it says is that if a quadrilateral has one pair of opposite sides that are congruent and parallel, then it is a parallelogram. That might have been the longest theorem that I've written. Almost went off the screen, but it didn't. So, what I need here then is a quadrilateral to look at. So here it is. And what I need to talk about is, so the interesting thing here is that I'm not going to be looking at two pairs of things. I'm just going to look at, let's go with AB and DC. So my given is that AB is congruent to DC and that AB is parallel to DC. And what I'm trying to prove is just that ABCD is a parallelogram. All right. So the way that I'm going to do this is how I've done most of these so far, is of course breaking this up into triangles. So the question is, how am I going to break this up? And just like before, we've done this a couple of times now, I'm going to draw in this diagonal here from A to C. And if I can talk about these two opposite sides or two opposite angles being congruent to each other, then I'll have enough to talk about this being a parallelogram. Now, I can be a little bit clever here and use one of these things in my proof here at the end of the day. And so I can look to either just prove something congruent or something parallel, but we'll see what is best for us later. So I'm going to go ahead and write down my given. So AB is congruent to DC. That was given. And then also AB is parallel to DC. So if I want to prove these two triangles congruent to each other, how am I going to do that? Well, let's mark the things I have. I guess that'd be a good start. Okay. So I've got the shared side, which would be an easy place to start here. So AC is congruent to itself. AC is congruent to itself by the reflexive property. All right. And then now what can I do? Let's see. So I think the easiest thing would be to use the fact that my lines are parallel here to talk about some angles, specifically these two, because they're alternate interior angles on these parallel lines. So I think that's what I'm going to do next. Statement number 4, angle BAC is congruent to angle DCA. And the reason for that will be because of the parallel lines. So if two lines are parallel, then the alternate interior angles are congruent. The alternate interior angles are congruent. And that comes from up here in 2. And so now I've got enough to prove these triangles congruent. I have side, angle, side. So statement number 5 will be my triangles. Triangle BAC is congruent to triangle DCA. And it'll be side, angle, side if the corresponding side, angle, sides of two triangles are congruent, then the triangles are congruent. And I will cite 1, 3, and 4. Okay, so now that I have these triangles congruent to each other, the question is, what's going to be the fastest way of me proving that this is a parallelogram? And I could go with proving that these two angles are congruent and then using the alternate interior angle converse theorem to prove that AD and BC are parallel. But that takes me 2 steps when I can really just kind of get to this in one. I'm going to say that AD and BC are congruent to each other. Statement 6, AD is congruent to BC. And I'll end up using not my definition, but a theorem to prove this. So, to prove that it's a parallelogram, not the statement here. So, AD is congruent to BC is my definition of congruent triangles. So, two triangles are congruent if and only if their corresponding parts are congruent. And that comes from 5. And so now I can use one of my other theorems here instead of using a definition. So I can say that ABCD is a parallelogram. And the reason for it will be that if a quadrilateral has 2 pairs of opposite sides congruent, then it is a parallelogram. And that comes from, this is a weird one, because I'm going to cite 6, but I'm also citing one of my givens back in 1. So it seems like I'm kind of cheating here that, I'm going to end up proving my final statement with one of my givens here, but oh well. It's just another way of proving that something's parallel, or a quadrilateral is a parallelogram, even though it's using one of the properties of my theorem here, and that's fine. So just to recap, so if a quadrilateral has 1 pair of opposite sides that are congruent and parallel, then it's a parallelogram. The way we showed that was just like we've done several times now at this point. We've broken this up into 2 triangles that we prove congruent to each other. Once we did that, we showed that then the last pair of opposite sides for this quadrilateral also had to be congruent, and so we used that theorem that says that if 2 pairs of opposite sides of a quadrilateral are congruent to each other, then it's got to be a parallelogram. So this is just one more way that I can prove that a quadrilateral is a parallelogram that I can now put to use.